Okay, so today we are going to continue with sequences, and we'll probably learn something new called factorials, which are interesting. And then we'll see where that takes us. So as a quick recap, yesterday we talked about sequences. We have two types of sequences. They can either be finite or infinite, which is, very straightforward, self-explanatory. A finite sequence starts and ends, that you can count how many terms there are. An infinite sequence goes on forever, it never ends. The natural numbers are an infinite sequence, 1 2 3 4 5 6. If you kept counting, okay, that would be an infinite sequence. Over here we have how we name the sequences. Okay, so we use usually A, but if we're talking about more than one, we may use B or C or, different letters. And we have those subscripts, right? So A1, A2, A3, and that goes on. And that just tells you what order that number comes in the sequence. Okay, so A1 would be the first term, A2 would be the second, A3 would be the third, right? And then we talked about yesterday, AN is called the nth term. Okay, and that's kind of how we kind of conceptualize what's going on. So there's two ways to, I don't know what you want to call it, carry out or identify or find the terms of a sequence. We can find it explicitly or recursively. To find a sequence explicitly, you use the term number to find the value of the term. Right, so there you just have an equation, and whatever your little subscript number is there, that's what you plug in here. And I'll plug in the numbers here to take a look at this in a second. Recursively, we talked about this briefly at the end of yesterday's lesson, but we didn't really get a chance to look at an example. And again, I'll do that shortly. But for a recursive function, we have to use the previous term to find the next term. All right, so here we can see a very basic example. And the names here, AN and AN minus 1, this just means the term before whatever we're looking for. So if I was looking for A5, well, that would be 2 times A4 plus 1. All right, so whatever number that is, this is just telling you you're taking that number and minus 1. So if we start with 5, then we need to use 4, right? And that goes for everything. All right, so as a quick warm-up, we're going to find the first 4 terms for both of these sequences. Let's make it 5 terms. Find the first 5 terms. So when we do that, I like to write it out just so we have it. A1, A2, A3, and I'll put here A4 and A5. So this one's an interesting one, and I wanted to take a quick look at it because here we have what's called an alternating sequence. Okay, and what I mean by alternating is it's going to change signs between every one. That's because we have this expression in the numerator, -1 to the nth power. Now, raising 1 to any power just gives me 1, but if I raise -1 to different powers, it's going to alternate. When it's an odd power, it's going to stay -1. When it's an even power, it's going to become +1. Right? So for a to the first, I would have -1 over 2 times 1. So that would give me 1/2. That was my first term. My second term, well, this would become +1 over 2 times 2. So that's, I'm sorry, this should be -1/2. So that is 1/4. A3 would be, again, -1 over 2 times 3, which would be -1/6. And usually after the first 2 or 3, you can kind of see the general pattern going on. So our denominator is increasing by 2 every time, and our sign changes. So A4 would be 1/8, A5 would be negative 1/10, and we can keep going on from there. And what I asked was for the first 5 terms. All right, so we start off negative, then we go positive. Oh, excuse me. Our fractions are getting gradually smaller. 1/2, 1/4, 1/6, 1/8, 1/10. Okay. Now for recursive, we need to use the previous term to find the next term. So our problem here if I don't have A1, then I can't do anything. Okay, well, for A1, I would need A0, and we don't have A0. Sometimes, sometimes A0, well, I don't want to say that because when we're talking about things like velocity and distance, we have V0, which means our initial velocity, or T0 is our initial time. But when we're talking about terms, we're counting them. So I can't have a 0th term. I can't start nowhere. Okay, this doesn't make sense. So for a recursive function, they need to tell you the first term. I can't find the second term without that first term. All right. So usually they'll tell you A1 equals some number. All right. So we're going to use A1 equals 3. So for A2, it's going to be 2 times my A1, which is 3 plus 1. So 2 times 3 is 6 plus 1 is 7. So now that 7 is what I'm going to use to find A3. It's going to be 2 times my last term, 7, plus 1. Well, that's 14 plus 1, and that's 15. Then for 4, I need to use 3. I'm going to have 2 times 15 plus 1, so that's 30 plus 1, 31. And then for my 5th term, it's going to be 2 times 31 plus 1, so that's 62. 62 plus 1 is 63. All right, so we have the first 5 terms there. All right, do we have any questions on how to find our terms for explicit or recursive functions? Or either or. Okay. So now let's talk about something slightly different, but it kind of fits in with what we're going to be doing overall. And that is factorials. Now, factorials are going to help us with some stuff that we learn later on, permutations and combinations, something called the binomial theorem, a lot of tools in math to kind of help us kind of take shortcuts with things like probability and number theory and what's called the counting principle. I think that's what they're called. It's been a while. Yeah, and something called mathematical induction, which is pretty much just making conclusions based on statements. So what is a factorial? You may have seen it So let's say all right. So we have some positive integer, okay? And this only works with positive whole numbers, right? Which is a positive integer. So 1, 2, 3, 4, 5. You can't do this with decimals. You can't do this with fractions. You can't do this with negative numbers. And, you know, with the context that we've been talking about, that kind of makes sense, right? This all has to do with what's called the counting principles. So, you know, when we're counting, although we have 0, which is, you know, the absence of a number, it's a strange concept mathematically, but we don't usually start counting at 0. We start counting at 1, right? So we're only dealing with positive whole numbers here, and the symbol for a factorial is an exclamation mark. Now you may have seen this if you've ever messed around with your calculators. With these calculators, you'd have to hit what is it? No, the probability button, PRB. It's out of focus. Yeah, I can't focus that. But you hit the PRB, and then you get a few different symbols there. I don't know if you can see it, but factorial is one of them. No, that's crappy quality. I apologize. But it is on your calculator. It is on graphing calculators as well. If you go into math, I think, yeah, and then in the probability section in math, no, again, maybe I should find an online thing for that. That might be helpful. All right, anyway, it's there, trust me. So n factorial is the product of all integers leading up to that number. So something like 4 factorial, that's telling me I'm doing 1 times 2 times 3 times 4. And that would get me 24. Right, so that's all you got to do for factorials is you multiply all the numbers leading up to whatever number is being factorialized. Right, so if I had 10 factorial, 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. And with factorials, you'll notice things get very large very quickly. 10 factorial, I wouldn't be able to do that in my head, but it is 3,628,800. All right. And then, you know, obviously 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 1 times 2 times 3. There is a special rule. Zero factorial is equal to 1. So it's kind of interesting. Factorial isn't really a function because both, oh no, it would be a function. Yeah, because 1 factorial also equals 1, but 0 factorial equals 1. That's a special case. And we see that, we might see that when we come out and do some probability stuff. We may end up with 0 factorial, and it can't be 0. It just wouldn't work. All right, so let's take a look at a a sequence with factorials. Okay. So you want to write the first 5 terms of the sequence defined by an equals 2 to the n power over n factorial. All right, so just like before, I'm going to write out 1, 2, 3, 4, 5. All right, so this is an explicit function, so all we're doing is we're plugging our n values in. All right, so this is going to be 2 to the first power over 1 factorial, which is 2 over 1, which is just 2. All right, so that one's simple. Our second term is going to be 2 squared over 2 factorial. Well, 2 squared is 4. 2 factorial is only 2. 1 times 2. So that also gets us 2. That's pretty interesting. Okay, the first 2 terms are the same, even though we clearly have, you know, a function that gives us different answers. A3 is going to be 2 to the third power over 3 factorial. So now this is where we got to be careful. 2 to the third is 8. 3 factorial would be 1 times 2 times 3, which is 6. So now we're actually decreasing. And my third term would be 4 thirds. Then a to the fourth, 2 to the fourth over 4 factorial. 2 to the fourth is, let me fix that, 16. 4 factorial, 1 times 2 times 3 times 4, we saw before, is 24. Okay, we can reduce this. I can divide both the numerator and the denominator by 8. And I end up with 2 thirds. Our fifth term, a5, I'd have 2 to the fifth over 5 factorial. 2 to the fifth, 16 times 2 is 32. 5 factorial would be 24 times 5, right? 1 times 2 times 3 times 4 gives me 24. Times 5 would give me 120. And we can divide both of those by, can we do 8? Yeah, I can divide them both by 8, and I get 4/15. All right, so the first 5 terms of the sequence are 2, 2, 4 thirds, 2 thirds, 4/15. All right, and we usually put the dots at the end. I think they're called ellipses, is the language arts term, just to show that it keeps going and that we're not going to end here. Right? We just found the first 5, but it doesn't end at 5, so you put the dot, dot, dot at the end. All right, any questions there? If you do not have a calculator, right, or like, you know, one of these calculators, if you're using online stuff, you can just type in the exclamation mark. It'll know what you mean. If you're using your calculator, well, here on my phone, it does have the factorial there. Remember, you might have to turn your phone into landscape mode to see the extra buttons. It should be there, factorial. All right, so it's just another tool in math, but it's, you know, it's something new. Any questions so far? All right, so there's one last thing that I want to talk about, and that's simplifying factorial expressions. So it may come a time later on where we're dealing with factorials in the numerator and in the denominator. Okay, well, you know, like I said, when we're doing whatever it's called, the binomial theorem, okay, we're going to be dealing with factorials. So what do I want to say here? I guess we'll just say simplify. Okay, so you may be given something like this: 8 factorial over 2 factorial times 6 factorial. Now, if we did it normally where I punched the numbers into the calculator, we'd get some very large numbers. Okay, 8 factorial is 1 times 2, you know. We saw 10 factorial was 3 million, so it'd be probably in the hundreds of thousands. But we can remember what this actually means. So what I'm going to do is I'm going to write out 8 factorial. All right, I expanded 8 factorial to what a factorial is, the multiplication of all the numbers leading up to that. And I'm going to do the same in the denominator. And when we write it like this, hopefully you notice we have a lot of common terms in the numerator and denominator. So just by writing it out, I can eliminate over half of the terms, right? So 8 factorial over 2 factorial times 6 factorial can be written as 7 times 8 over 1 times 2. And I could go ahead and I can do this, but I can simplify this even further. Right? This is 2 down here. I can do 8 divided by 2 is 4. 7 times 4 is 28. All right, so all of this, 8 factorial, you can punch it in your calculator, but be careful. You'll get very large numbers. You know, make sure you use parentheses if you're doing it. But if we just write it out, it becomes a lot easier once we simplify. Right? We could have also just done 7 times 8, which is 56. 56 over 2 would get us 28. So either way, we got that. All right. So I did say, you know, I'm not going to give you guys any homework for now until the 3rd marking period ends. So, I mean, I don't know how you feel. I do feel that these are fairly simple concepts, even though they are, you know, they're new to you. You may have been familiar with them, but I'm not expecting you to have seen them or to know how to deal with them. But I don't think they're very complicated concepts. So if you would like some extra practice, you can shoot me an email on the side and just say, hey, Mr. Murray, I want to try a few examples. But in the meantime, just again, like I'm going to repeat this all week. Please make sure you're making up any missing work before Thursday. The marking period ends Thursday. All right, guys. So yeah, so if you have any other questions about this, or if you'd like to do some practice, shoot me an email. Otherwise, that is it for us today, and I will see everybody tomorrow. Have a good one.
Mr. Murray,
What's up?
do you know if...
1 second.
Alright.
I don't know what happened to my mouse. It's gone. Okay, yeah, we're good. Go.